Otherwise, I will continue, and during my explanation, if you had any question, please stop me, raise your hand and stop me, and you can ask your questions. Okay. So now, do you have any question regarding the problems? Okay. So we start the first problem. For the instant represented when crank OA, this link passes the horizontal position exactly at this position, determine the velocity of the center G of link AB. Here, this is the center of the link AB. We have the angular velocity for this link OA, which is 8 radian per second. So we can obtain the velocity of each point on this link because this is a pure rotation motion. So easily, if you want to find the velocity of each point on this link, the velocity is equal to r times by omega, which omega is 8 radian per second, and r is the distance from the point and point O. Here we need the velocity of point A, that we call this V sub A. You know that VA at this instant, because link OA is completely horizontal in horizontal condition, so VA is perpendicular to this link, so VA is vertical at this instant. To solve this problem, we can solve this with two different methods. First, using the instantaneous center of zero velocity, and second, using the relative velocity equations. So first, let's start to using the instantaneous center of zero velocity. For this purpose, we need to obtain the direction of the velocity for 2 points. Here we want to obtain the velocity of point G, which is located on the rigid body AB. So we need to find the instantaneous center of zero velocity for link AB. Yes. So in this link, we need to obtain the velocity direction for two different points, which here in this example, the best option is point A and B, because we know that at this instant, point A is rotating about point O, so its velocity is vertical, as I told you, and point B is moving in the slot, so its velocity is horizontal. So we can plot two perpendicular line to the VA and VB, as you can see, and this point, which is the interconnection point of point A and B, is the instantaneous center of zero velocity. Now we can find, using the velocity of A, we can find the angular velocity of AB. So first we need to find the velocity of point A in link OA, because A is a point, a common point between link OA and link AB. So the velocity of A, when you look at this from link OA, it's equal to the 8 radian per second times by its r, which is 60 millimeter, or 0.06 meter. Here, this is the velocity of point A, and the direction is clear. It's in upward direction and it's completely vertical. So the velocity of A is 0.48, and now we can find the omega AB, because point A at the same time is a point on rigid body AB, and we know that this is the instantaneous center for link AB. So the velocity of A is equal to angular velocity of AB times by this length, which is RCA. Okay, the RCA, you can easily find RCA because we have some geometrical information. If you plot that this triangle ACB here, ACB, okay, sorry for the interruption. One of your friend has problem with the link of Zoom. Okay, so in this triangle ABC, you can easily find the angle alpha and theta because we know that this length is 90 millimeter. This is 90. This is CB, and okay, and link the this length is 90 plus 90, 180 BA. So easily we can find alpha, theta, and the length CA. So this is from the trigonometry relation and the geometry of the problems. You can obtain that CA, how much is the CA, and also you can find the angular velocity for link AB. Okay, so here from the trigonometry and from the geometry, you can easily find RCA, or the distance between point C and A. So we know the velocity of point A from the link OA. And the next step, easily you can write that the velocity of A in link AB is equal to RCA times by omega AB, because as you know, the instantaneous center of zero velocity means that we can assume that this link at this instant is rotating about its instantaneous center. So at this instant, we can assume that link AB is rotating about point C. So it means that we can find the velocity of point A by using the angular velocity of link AB. Okay, so from here we can find the omega AB, or the angular velocity of link AB, which is equal to the velocity of A divided by RCA, this term. And finally we can find the omega, we can find the angular velocity of link AB. So when we have the angular velocity for this link, now we need to find the velocity of point G, which point G is exactly at the center of link AB. For this purpose, again, we need to obtain the length CG. And again, from the trigonometry relations and from the geometry of the problem, you can use and find that CG is equal to CB is equal to BG, because in this triangle BCG, all of the angles are equal, and they are equal to 60. So again, VG is equal to omega AB, which we obtained from the previous part here. This is the omega AB. So VG is equal to omega AB times by RCG, which RCG is obtained here. So this is the instantaneous center that we obtained the velocity of point G, but this is in just a scalar parameter, or this is the amplitude of the velocity. The second method is using the relative velocity, as I told you. Using the relative velocity, first we need to obtain a coordinate system. We consider that this is the x, y, the coordinate system. Using this coordinate system, we can write the velocity of point A and B. The velocity of A in vector form is equal to omega OA cross ROA. Using this coordinate system, if you want to write omega, this 8 radian angular velocity, if you want to write it in vector form, and using this coordinate system x and y, this is the x and this is y, if you want to write omega in vector form, it will be minus 8k, because the direction is in z direction and it will be in negative direction of z axis. So it will be minus 8k cross, what is the position vector, ROA. ROA is, again using the x and y coordinate system, is minus 60 millimeter in x direction. So it will be minus 0.06 I. So here we can substitute. And finally, the velocity of A in vector form is 0.48 J. In previous part, we used a scalar form, but here we are using the vector form of the velocity. So the velocity of B, again using this coordinate system, here you can see that B is moving to the right hand side. So to the right side, which is the positive direction of x-axis. So VB in vector form is equal to VBI. And then we can write the velocity equation between point B and A. From the relative velocity equation, we will have VB, which is equal to VA. This is VB, VA plus omega cross RBA. So omega BA is the unknown. We want to obtain the angular velocity for link AB or BA. We assume that omega BA is equal to omega K, and we want to obtain omega because we know that when this system is rotating, the link OA is rotating in clockwise direction, the link AB will rotate in counterclockwise direction. And again, using this coordinate system X and Y, we can conclude that omega BA is equal to omega K. So the direction will be in positive direction of Z axis. And now we can substitute and find the omega. And the other point is we need to obtain RBA. RBA is the position vector of point B with respect to point A. It means that you should put this coordinate system on point A and then find the position vector of point B with respect to this new coordinate system. And if you use this relation according to the geometry of the problem, here you can see the length AB is 0.18, and here this angle, you can find the angle theta here, the angle theta, or you can find this angle, and then you can use the geometry of the problem and find RB with respect to A. Now you can substitute into the equation and find the relation between the velocity of B and the angular velocity. As you know, this is a vector equation, which in fact this is a two equations with two unknowns. So you can solve these two equations at the same time to obtain the two unknowns. From the I component in the left hand side, we have VB, and from the right hand side of the equation, the I components will be 0.09 times by omega. And for the J, we have this term in the left hand side is 0, and in the right hand side we will have 0.48 minus 0.155 omega. So from this second equation, you can obtain omega and then obtain the velocity by substituting into the first equation here in this equation. And when you substitute here, you can obtain the velocity of point B. The next step, we need to find the velocity of G with respect to point A, because this time we have the velocity, the angular velocity of link BA. And if you substitute in this equation, VA, we have the VA, we have omega BA, because here we obtain the omega BA. This is the omega BA. So we have this term, and RGA, which is again from the geometry of the problem, RGA, when you put the coordinate system on point A, you can find the position vector of G, which this length is 90 millimeter. Okay. And the angle again 30. This angle is the angle of this link with the horizontal is 30°. So you can easily substitute and find the position vector RGA. Now you can simplify and solve this equation, and you can extract the velocity of point G in vector form. This is the velocity of point G. Yes, but this is in vector form. And if you find the amplitude of this vector, it's equal to 0.277 meter per second. Okay, so the amplitude is exactly the value which is obtained in the previous method, but here we obtain the velocity of G in vector form. Okay, any question from this part? Is it clear? Any question? Okay, so the second problem here, we want to determine the angular acceleration of link AB and the linear acceleration of A for theta is equal to 90°. When this angle, this is the theta, this angle is equal to 90°. Theta dot is equal to 0, and theta double dot, which is the angular acceleration, is 3 radian per second square at that position. So in this condition, we want to obtain the velocity, the acceleration of point A, this point, and also the angular acceleration of link AB. This is the link AB. So at this moment, we can write the velocity of B, this point, the velocity of B, which is a point on link OB, and link OB is rotating about point O. So you can easily find the velocity of B, which is equal to omega OB cross RBO or ROB. But the angular velocity for this link at this moment is 0. Here theta dot is 0. So we can conclude that the velocity of point B is equal to 0. The acceleration for link OB is equal to 3 radian per second square. And using this coordinate system, X and Y, and using the direction of theta, so it will be minus 3k. In link AB, in this link, which is a rigid body, we can write the relative velocity equation between point A and B. If you write the velocity of A, it's equal to the velocity of B plus omega AB cross RAB. And omega AB, if we assume that omega AB is rotating in the same sense of link OB, we can assume that this is K. The direction is in positive direction of Z axis. So RAB, if we call it that RAB at this moment is XI plus YJ, which X and Y are two unknowns value. I mean, when point B or link OB is in horizontal condition, we can find the position of link point B with respect to point A. But we don't need to calculate this. So we assume that RAB is XI plus YJ. So if you substitute into this equation, the velocity of B is 0 from here, because the angular velocity for link OB is 0. Omega AB cross X plus Y is equal to X omega AB minus Y omega AB in Y and X direction. But the velocity of A, the velocity of point A, as you can see, this slide there is restricted to move in this slot. So the velocity of point A is only in horizontal direction. So in the left hand side of the equation, the left hand side, we will have VA times by I. It means that the velocity of A only it has a horizontal component or the component in x direction. So we will have VA times by I is equal to x omega ABJ minus y omega ABI. So we have again two equations. The coefficient of I is VA is equal to, this is the coefficient of I, and in the right hand side of the equation we have minus y omega AB. In the left hand side the coefficient of J is 0, and in the right hand side this x times by omega AB. So this is the second equation. If you look at the second equation, x omega AB is equal to 0, we can conclude that omega AB is equal to 0 because x is the x component of the vector BA. Definitely, this component is not 0 when B is in horizontal condition. So okay, my because I'm using a USB slot for the Zoom, in 10 minutes later our session will be finished, and if we couldn't finish these problems, I will continue again, and I will again join this session with the same link, and you can join me again after this session. Okay, so I try to finish this in these 10 minutes. So here, from this term, we can conclude that omega AB, or the angular velocity for the link AB, is equal to 0. And finally, we can conclude that the velocity of A is equal to 0, because in this first equation here, when omega is 0, so VA is equal to 0. The next step, we need to obtain the acceleration for point B, which is equal to omega OB cross omega OB cross RBO and plus alpha cross R. Again, if you substitute here for point B, we know that the angular velocity is equal to 0. So this term is completely 0, and we can substitute instead of alpha and RBO. So the acceleration of point B can be easily obtained. Then we can substitute into the relative acceleration equation here, because the angular velocity for link AB is equal to 0. Here we obtain that this is the omega AB. So here you can substitute omega AB is equal to 0, and then you can obtain the acceleration of point A and the alpha of AB, or the angular acceleration of link AB. So you need only substitute and simplify, because the acceleration of point A here, again, similar to the velocity, we know that the acceleration of point A is in horizontal direction. So we assume that acceleration of A is A times by I, because it uh, only has a horizontal component, or a component in x direction. So you can substitute here. Again, we will have two equations with two unknowns, and you can solve it for x and y. When B is in horizontal position here, you can obtain x and y, the position vector of B with respect to A. Here we substitute x and y in this equation. For the second part, when you want to obtain the acceleration of point A, we need to obtain x and y. From the geometry you can easily find it, and then you can substitute and solve these two equations. The first equation for I is A is equal to minus 0.4 alpha AB, and the second equation is 0 in the left hand side, and in the right hand side we have minus 1.2 minus 0.3 times by alpha AB. So by solving these two equations, you can obtain alpha AB, which is minus 4k, and the acceleration of point A. Okay, and finally the last problem, for the instant represented link CB is rotating counterclockwise at a constant rate 4 radian per second, and its pin A causes a clockwise rotation of the slotted member ODE. Determine the angular velocity and angular acceleration of ODE for this instant. So in this problem, when we have a pin which is moving in a slot, I solved an example like this in the problem, in the examples in the lectures. In this type of problems, you should consider one point which each coincident between two different links. We can consider point P here on link ODE, which coincident with pin A. So at here at this point A, we have two imaginary points. One is P, which is located on link ODE, and the other point is the pin A at this instant. So put the relative coordinate system on point P. So we can write the velocity of A with respect to point P using a relative coordinate system. So VA is equal to VP plus omega cross R plus V relative. So here we are using a rotating coordinate system, rotating relative coordinate system. So we will have this term. Omega is the angular velocity of the relative coordinate system, and R is the position vector. Because point A and P at this instant are two, P is a coincident with point A, so R is equal to 0. So this term is 0. The relative velocity is the velocity of point A or pin A with respect to the system attached to point P. So the direction of V relative is exactly in the direction of the slot. As you can see here, this is the V relative, and VP is the velocity of point P, which is located on link ODE. VA is clearly obtained from the uh, given data. We know that the velocity of pin A, which is located on link CB, we have the angular velocity, so you can obtain the velocity of point A. VP is at this instant when link CB is rotating in counterclockwise direction. So the link ODE again will rotate in clockwise direction. So we can find the direction of VP using the direction of the angular velocity. When you substitute here, we have also the direction of the relative velocity. We have two unknowns. One is the VP or the amplitude of the velocity of point P, and the other one is the amplitude of the relative velocity between point P and A. So you can substitute, and we will have again two equations with two unknowns. By solving these two equations, you can obtain the VP and V relative. Okay, so this is the relative velocity and this is the VP. So link ODE, you can find the angular velocity for the link ODE, because when you have this velocity VP, you know that P is an imaginary point on link ODE. So because this is a pure rotational motion about this point O, so the velocity of P is equal to the radius of point P, which is this length, times by angular velocity. So you can obtain the angular velocity easily. And then for the acceleration, again, we have the same equation using a rotating relative coordinate system. The acceleration of pin A is equal to the acceleration of P plus the relative acceleration. Again, the relative acceleration, the direction of this acceleration is the same as the direction of V relative. It's exactly the direction of the slot in link ODE. So we have the direction for the relative acceleration. The alpha ODE is equal to 0 because, because the radius is 0. So the alpha cross R is equal to 0 because P is coincident with point A. And for this term, again, because R is equal to 0. So in this term, again, omega cross R is equal to 0. And finally, 2 times by omega times cross by V relative. We obtain the V relative in previous part. Here we obtain the V relative here. And omega ODE, which obtains here, which is 4 radian per second. So we can substitute and again obtain two unknowns because we have two unknowns, which is relative, the acceleration of A with respect to P and the acceleration of point A. So you can substitute and find two unknowns from this equation with two equations and two unknowns. Okay, so again, we will have here two equations for I and J. You can substitute and solve for A relative and for the alpha, which alpha is the angular acceleration for link ODE. Okay, I think there's just, you should use some calculations and then you can find the response. Any question? Because we don't have time, or time is almost finished. Any question from this part? Okay, so because the time is finished, we can wrap up this session. If you have any question, you can ask me in the Viber, or you can send me a message in Viber or email. Okay, thank you and have a good weekend.